Today I'm gonna talk about nothing. Well, not really nothing, but about vacuum. And we asked the question, does a vacuum really suck? Usually we are surrounded by particles. Atoms and molecules vibrate according to their temperatures and constantly knock against each other and against us. Ow! But when we take a closed box and pump out all the atoms and molecules, we can almost achieve a vacuum. In a near vacuum, all sorts of interesting things happen, undisturbed by particles. I want to look into these effects and clean up a few common misconceptions about vacuum. Don't worry, I will not go into quantum mechanics, but I will try to keep it simple. But before we talk about the vacuum, I need to say a few words about the particle world. Let's start with Newton's first law. Force equals mass times acceleration. We need a force to accelerate a mass. If there is no force, there is no acceleration. And if an object is not accelerated, then it is either at rest or has a uniform straight motion, forever. Or would such a motion make sense? No. But when a force is applied, it does make sense. But when I kick a ball here on Earth, why doesn't it roll forever in a uniform straight motion? Because there are forces acting upon it. Air resistance, friction, and if you are lucky, the goal net. The cool thing about a vacuum is you don't have friction, you don't have air resistance, and if you are in space, even gravity can be pretty small. In the particle world, particles constantly knock into each other. But what exactly happens when they do that? They exchange kinetic energy. Or we could say they exchange momentum. The momentum is defined as the product of mass times velocity of a body. If a massive body knocks into a light body, it gives it a lot of velocity. That's why they use iron clubs for long distant hits in golf. Now let's imagine a box full of particles, for instance a gas. The molecules wobble and fly in all directions. They constantly bump into each other. And some of them also bump against the wall of the box. This creates pressure. The more molecules in the box are that can hit the wall, or the higher their energy, the higher is the pressure against the wall. And high energy means high temperature. So now that we have looked at the theory, we can start to tackle the question from Brian M.
Say the shuttle's over here somewhere. This is just one of those little nozzles, tiny little nozzle that shoots compressed oxygen out into space. Okay? And remember though, space sucks.
Sorry to interrupt you, Brian, but space does not suck. There are a lot of other things that do suck, but not space. I will explain it to you later on after you have asked your question, okay?
So you have this pressure acting the other way. What that pressure is really not important because it sucks. That's all that matters. So we have all this suction happening on the engine. And on the engine and on the, or not on the engine, on the nozzle, excuse me, and so just pull it on here and say the nozzle's closed right now. This nozzle isn't active yet. And so you have this built-up compressed oxygen inside this nozzle, and say there's a tank over here filled with compressed oxygen. And when they open the end of the nozzle, or the jet, whatever you want to call it, you have this suction force over here, and then I'll use red to show that the very high pressure oxygen wants to spray out into space. But space is already pulling away from that oxygen. So how do you develop an equal and opposite reaction when space is already pulling all of this stuff away? It's sucking, it's pulling. So this opens and there's compressed, built up oxygen in here, and the oxygen is actually pushing on the wall of the nozzle and the tank that it's in. Okay? It's already pushing on that surface. And then it opens and it sprays out into space, but there's no air out there. There's no positive pressure to hold air against the oxygen if there was any air. And so it would just, in my opinion, I mean, when you really start to think of it, wouldn't it just expand infinitely the moment it starts to come out? Where's the opposite reaction created?
Thank you, Brian. If you think a vacuum sucks, you look at the world the wrong way round. You are like a ghost driver who thinks all the others use the wrong lane. A vacuum is, simply speaking, nothing. How can nothing suck something? Here's your rocket engine. Inside is a compressed gas. For those little steering nozzles, it usually is helium. There are lots of molecules inside the nozzle or its tank. They all wobble around. When you heat them up a bit, they wobble even more. They bump into each other and against the wall of the tank. This creates pressure. There's nothing pulling from the outside, only pressure from the inside of the tank. And now let's open up the back of the nozzle. What happens? Suddenly, in one direction, there is no resistance against the molecules anymore. Nothing that kicks back the helium inside the tank. And so the molecules can fly away. The gas pressure pushes against them from the inside. The particles of the exhaust gas fly backwards. Can they go everywhere? No. As long as no force acts on them, they will move in a uniform straight motion. It would take a force to change their direction. But which force? Remember, vacuum is nothing. And so only when they knock against each other, they may disperse a bit. And now to the second part of your question, Brian. Does a rocket need air pressure around it to work? No. Each molecule that is pushed out of the nozzle pushes at the same time against the rocket, and only at that time. When it is only a millimeter away, it has no effect anymore and just flies through space on its own. Actio equals reactio happens exactly when a molecule leaves the nozzle. The momentum of the exhaust gas creates an additional momentum for the spacecraft into the opposite direction. Momentum is mass times velocity, so you can either push away a lot of mass, which in turn makes the spacecraft more massive as well and more difficult to push, or you push away the exhaust gas at a high velocity, for instance by heating up the helium. And now let's have a look at a rocket booster on Earth, or in air. We have all these air molecules around our booster, and they exert a certain pressure from the outside. When we open the nozzle, exhaust gas is streaming out. As soon as it hits the outside air, it accelerates air molecules away from the machine. These bang into other air molecules and transfer some of their energy. But does the exhaust particle exert a force onto the machine after hitting the air? No, not really. Let's have a close look at what is happening here. We have an air molecule and an exhaust molecule. The air molecule just hangs around and has a low momentum, whereas the exhaust molecule shoots out the engine at high velocity and thus has a big momentum. When the exhaust molecule hits the air molecule, it loses a bit of its momentum, while the air molecule gains a lot of momentum. The air flies away like a pool ball into the backwards direction, and the exhaust slows down with each collision. Air flying away cannot exert a forward force onto the engine. Perhaps a wall could make the molecules bounce off and push the engine a little bit forwards, but the effect will be tiny. You would need to enclose the engine to achieve more push. And there is another problem. Air resistance not only decelerates the plane, but also might decelerate the exhaust while leaving the nozzle, lowering its momentum a bit, so that the reactio may also be lowered a bit. In the vacuum of space we do not have these slowing down effects, and so tiny little booster nozzles are sufficient to steer a big spacecraft. In his video, What Happens When You Put a Drone into Vacuum? Can It Still Fly? Hydraulic press action guy also shows a balloon propelling itself forward by letting out air. It shows the rocket propulsion, but I wish somebody would repeat this experiment in a bigger vacuum chamber, so no one can say the balloon is pushed away from the wall. There are a lot of guys out there who try to prove that rocket propulsion needs an outside medium like air to push against, to make the rocket fly forwards. And they put up experiments on YouTube as undeniable proof. Let's look at one of those experiments.
So now to the interesting part, because I'm going to demonstrate in this next test that a mass most certainly is required to make a rocket move, or a balloon move in this case. So I'm just going to put up on the screen again the quote that the guy made earlier that I asked you to remember. It doesn't need to be able to push on anything to make it transit, is what he says. So I've taken a piece of paper and I've wrapped it around the rear end of the balloon and taped it top and bottom. So the nozzle is sort of in the curve of the paper there. So when I let go, the air will still escape from the balloon at the same speed. The balloon will deflate as quick as it did without the paper. So according to his quote earlier, this should still move, this should still transit at the same speed, because it's not reliant upon it pushing on anything. It's the mere fact that air is released from the nozzle that provides the reactionary force to propel the balloon. So let's have a look at what happens. So Newton's third law experiment, test 2. Well, that didn't move very far.
Okay, what happens here? The very moment an air molecule leaves the balloon, it gets pushed away and also pushes away the balloon. Actio equals reactio. That's the principle of rocket propulsion. We get a forwards momentum. Let's put it up here so we don't forget it. But what happens next? The air molecule that is not attached to the balloon anymore flies backwards on its own until it bangs into the paper sail. There it transmits its momentum at the sail and creates a backward momentum in the balloon sail system. Now we have a forward and a backward momentum that cancel each other out. The balloon will not move. This experiment does not disprove rocket propulsion, but mathematically even proves it. Because if you would blow against the sail from the outside, the balloon would move backwards. In the experiment, it does not. because the forwards momentum of the rocket propulsion contracepts it. When I was a boy, I had a revolutionary idea. What if I put a propeller onto a sailing boat? Shouldn't it blow the boat forwards? So I tried it with an electromotor propeller. But it did not work. The boat didn't move. I found out that the propeller without the sail would push the ship backward, but the air blown into the sail cancelled this movement out. The idea did not earn me pockets full of money, but I had learned something about physics. And it was the same problem as in the balloon experiment. Another question along a similar line is, if Earth was a ball in the vacuum of space, our atmosphere would be sucked away. Or pressure tends to equalize with its surroundings, always, everywhere. Or even, how did the very first air molecule survive the incredible surrounding vacuum? Okay, let's have a look at our atmosphere, or rather at a single air molecule. It basically has three options: rise towards space, stay at a certain height, or fall towards Earth, depending on the forces acting on it. The force that pulls it down is gravity. Most air molecules fall down. That's why the air pressure is greatest near Earth's surface. One upward force that could fight the pull of gravity would be the centrifugal force. Again, we have three possibilities in this system. Gravity wins, the molecule sinks. Centrifugal force wins, the molecule flies up towards space. Or gravity and centrifugal force are equal and cancel each other. The molecule just floats around. When we take the third case, we can calculate the minimum orbital velocity of an air molecule when it just fights off gravity. We look up the formulae for gravity and centrifugal force and set them equal. The mass of the molecule is found on both sides and can cancel out. We also can erase one distance on both sides. The simplified formula is easy to use in a pocket calculator. We find the minimal orbital velocities for air molecules at different heights. Almost 8 kilometers per second. This is a pretty high velocity for an air molecule. Only a few get that fast. But there is another force that can push an air molecule into space: collision energy from other air molecules. Most molecules of our atmosphere bump as well into lower as into higher molecules and won't get much push upwards. But the ones in the outermost layers can get a lot of push, so that they might travel a bit into space. But as long as they don't reach about 12 kilometers per second escape velocity, they will soon come back. Our atmosphere is safe from the surrounding vacuum of space. Let's come to the next question. Can rockets burn fuel in space? Most people say you cannot burn anything in space because there is no oxygen in the vacuum. And they're right. But some people go even further. They claim even with an oxidizer you wouldn't be able to burn anything in space.
So how about something that has its own oxidizer, such as gunpowder? See, this is a mixture of charcoal, sulfur, and potassium nitrate. When heated, the potassium nitrate gives off oxygen, which the sulfur and charcoal uses to burn. So I've got a little bit sitting in there. Let's apply the laser goggles, and let's light it off. first in the atmosphere and then in the vacuum. Okay, as you can see, it produced lots of smoke and burned rather quickly. Most of the air is now gone. Let's see what happens. The gunpowder did not ignite.
So what happened here? In the first part of the experiment, the laser shone directly onto the gunpowder. But in the second part, it shone through a window. So it's no wonder it had less energy to ignite anything. But even if he had put the laser right into the box with the same outcome, it only shows that you can't ignite gunpowder with a laser in a vacuum. That means rocket engines have to be a bit more complicated than that. Let's look at some chemistry. Two molecules have to come very close together in order to exchange electrons. And in most cases, it takes some activation energy as well to start a chemical reaction. When molecules are too far away from each other, they usually won't react. That's the reason why the laser experiment did not work in vacuum. In air, there is oxygen all around, but in the vacuum it only can come from an oxidizer. Loose gunpowder means a too long distance between molecules. And when the door is closed, a lot of the activation energy from the laser just gets reflected. No wonder the gunpowder did not burn. So how did they do it in real life? They use liquid oxygen and liquid hydrogen, two heavily compressed reactants. In some rockets they use RP1 instead of hydrogen. The principle is the same. They heat up the reactants, though they become a gas again, and pump them under high pressure into the thrust chamber. There are many outlets for the gases, always in pairs, one hole for the oxidizer, one for the fuel. This way the molecules get close together. Now they only need an activation energy. The F1 booster that is used in the huge Saturn V rocket uses a 500 volt spark from the augmented spark igniter to start the reaction. This is a simplified animation. In real life they pump tons of reactants into this chamber each second. The gases react, and the chemical energy that is released from the reaction lets the exhaust move away at high speed, pushing the rocket forward. Another question concerning the vacuum of space addresses spacesuits. Won't they explode in space?
The point of the whole thing with the astronaut suits is that technically they should explode when they are, entered into a vacuum environment. Now, what NASA claims is that the spacesuits are designed to expand a little bit, when they're out in the vacuum of space. But the fact is that they're made out of I want to say, less than a 1/4 inch thick.
3/16 inch.
Yeah, 3/16 inch thick material that's 11 different layers of fabrics. Now, I'm sorry, but let me put it to you in this perspective. Do you think that you could make a vacuum chamber out of 3/16 inch material fabrics? And the answer to that is, of course, no.
No way.
You have to have structural and tensile strength in order to allow for a spacesuit that's going to enter the vacuum of space. And really, the only way that this could possibly work is if you have a pressure neutral spacesuit enter the vacuum of space. So what that means is that the interior pressure of the spacesuit would have to be a near perfect vacuum. Then they could go out into the vacuum of space and it would still expand, but then that doesn't work. I mean, your body has to be under 15 pounds of pressure per square inch in order for us to survive, because that's what we're used to. So this idea that NASA was sending up sewn together, and the old ones were one piece, but they were still sewn together. The new ones have interchanging parts, but essentially sewn together or slapped together fabrics, entering a near perfect vacuum without exploding, just completely debunks. It totally demolishes the idea that they've been to this so-called vacuum of space. Now,
When I heard that, I wondered, why on Earth, or rather, why in space should a spacesuit explode? But then I remembered Brian.
Okay. And remember though, space sucks.
First of all, let me assure you, space does not suck. Let's have a look at the spacesuit. Very close. It consists of a multi-layer fabric of about 1/4 of an inch thickness. Can that thin stuff cope with the extreme pressure? What extreme pressure? It only has to cope with 1 atmosphere. The same pressure that your skin has to cope with. Have you seen anyone implode here in our atmosphere? So why should 1 atmosphere make a spacesuit explode? When a fabric has to survive 1 atmosphere, this means it will not rip when you put a weight of 14.5 pounds per square inch on top of it. Is this much? Well, waterproof outdoor fabric has a resistance to a water column of up to 29 pounds per square inch. So I am pretty sure that high-tech spacesuit material also can cope with 1 atmosphere pressure. It will not explode. So now let's come to the next question. Is it really cold in space? Or, as this guy reverses the question so eloquently,
Hey yo, how you doing? It's your one and only best friend, Reverend Tacos Guidos Bedarinos. Hey, but I thought you knew this already.
Alright people, let's talk. Subject. NASA's lies exposed. The sun is not hot. It's cold fusion. Alright people, let's talk. There's something you need to know about the sun. We are told that the sun is hot. Well, if the sun is hot as we are told, shouldn't the sun burn up all the objects, planets, and our astronauts in space? Think about this. Think about this. I can't stress enough. Think about this.
first we have to find out what is temperature. Temperature is undirected kinetic energy. You could say it makes the molecules wobble. Give it more energy and it will wobble faster. But where does this energy come from? Well, a molecule can either absorb electromagnetic radiation or kinetic energy from other molecules that bump into the molecule. So what can heat you up in space? Electromagnetic radiation and the kinetic energy of other molecules bumping into you. Let's start with electromagnetic radiation. There are all sorts of radiation. Depending on the wavelength, we have gamma rays, X-rays, ultraviolet, visible light, infrared, microwave, and radio waves. A molecule can either absorb, emit, or reflect radiation. Absorption makes a molecule take in energy. It wobbles faster. If a molecule emits energy, it wobbles slower. Reflection does not affect the temperature of the molecule. So how much energy can be absorbed? It depends. For instance, on the distance between the source of radiation and yourself. Let's have a look at a candle. When a candle burns, it emits energy into all directions. The energy of the candle gets dispersed. The further you are away, the less energy you can absorb. The energy amount decreases with the distance squared. That is called the inverse square law. And that's why planets closer to the Sun are hotter than planets further away from the Sun. But not only distance, but also reflection influences the absorption rate. The more you reflect, the less you can absorb. That's why temperature-sensitive parts of spacecraft are often wrapped in gold foil. In astronomy, the measure for the reflection of a planet's surface is called albedo. Planets with a bright surface, that means a high albedo, reflect more radiation and cannot get that warm. Darker planets have a low albedo. They reflect less radiation and absorb more energy, so they get warmer. But we talked about another way to absorb energy, by molecules bumping into us. Luckily, there aren't that many molecules in the vacuum of space. So, even though the ISS is flying in the thermosphere, where it is about 400 degrees Celsius, there are only a few molecules around up there that could bump into you, because the density up there is about 1/1,000,000th of that what we have here on Earth. So don't worry, our astronauts are safe.
Roger, 0J, and I feel fine. Capsule is turning around.
Okay,